Hello and welcome to our next lesson of functions and applications, where today we are looking at key features of quadratic graphs. So today we're going to be comparing the three representations of the quadratic function, so standard form, vertex form, and factored form. And we're going to see when these equations are best for us to use and what information can we determine from each function. So first, let's consider the parent function of the quadratic function, which is just our x squared function. And here we have its graph. So starting with the vertex here is just 0, 0. Our axis of symmetry is x equals 0, and our direction of opening is upward. And our x-intercept, so here you can either write x is 0 or the point 0, 0. Both of these will be acceptable. And same with y-intercept. It's at y0 or 0, 0. And our now we have a new concept, which is increasing and decreasing intervals. So you've seen it before, but we haven't really used it as much when we were interpreting quadratic graphs. So we're going to see it today. But it's pretty much we're looking at our graph and seeing for what values is our graph decreasing and for which values is it increasing. So here we see that as we are coming towards this side from the left, we go from our negative numbers towards 0, we are actually decreasing. And then at 0, we turn and we go upward, so we are now increasing. So we have a positive interval there. So here, when we are writing our intervals, we are using set notation. So here, x is in R, and this is all values of x less than 0. Oh, sorry, that's for decreasing. And for increasing, we have all x real numbers, and x is greater than 0. And so now you might be thinking, what about 0? And 0 is actually called a turning point. So it is the point for which your function switches from increasing to decreasing. So at that point, it's not neither increasing or decreasing. It's simply the turning point. And so let me just add that there. Turning point is 0, 0. So now, a question for you is how do transformations of the graph affect its key features? So consider the transformations we've seen so far. For example, if I move this graph or this parabola upward, so I translate 3 units to the 3 units up, then I notice that my vertex has changed as well as my y-intercept uh, and my x-intercept. So we would, in that case, see that we actually have no x-intercept. Our y-intercept would be at 3, and our vertex would be at 0, 3. And things that would remain the same are the axis of symmetry, the direction of opening, as well as their increasing and decreasing intervals. So now take a moment and think about all the other transformations we've seen and consider how making those transformations would affect these specific key features of the quadratic. So now we have a little bit of a put it all together where we are comparing the three forms of the quadratic formula and to analyze which is best and when. So I have a little word bank here for you now, which we can use to fill in the blanks here. So starting with our standard form, ax squared plus bx plus c. What information is easy to see here? So take a moment to think. And starting with A tells us first the vertical stretch and compression. So based on the value of A, if A is so we saw when A is less than 0 or when A is between 0 and 1 or when A is greater than 1, we have a vertical stretch or compression. We also saw that A tells us the direction of the opening. So when A is greater than 0, we have that the parabola opens upwards, so it's positive upwards. And when A is negative, our parabola opens downward. Now for C, So first, see what we have to analyze here is what about the other two terms? So ax squared and bx. What's special about those two terms is they both have that x in common. And we would think, what happens when x is 0? Such as when we're finding the y-intercept. So when we do that, we are only left with c. Oh no, it's okay. Let me move that g back. Um, so it tells us the y-intercept. Now, to determine the vertex, that's already there, but we need to either factor if it is possible to factor, and that way we get our factored form, and that tells us the roots, which gives us the axis of symmetry, and from there we can find the vertex. Or you can try to complete the square to get it into vertex form and try to get the vertex there. And I guess one last option there could be to graph it, but typically, and especially for the problems we're going to see moving forward where we have application of quadratic functions, it's really hard to graph them manually. And as you will not be using graphing tools for many of your assessments, typically we leave that out. So try factoring or completing the square. So when is the standard form best for us? It's best when we are performing algebraic manipulation. So if we need to go from a form to another form, it's always best that we start with standard form because from there it's easy to go to the vertex form and it's also easy to go to the factored form. And it also helps us when we have to apply the quadratic formula or the discriminant formula. So recall for both of those, we require to know A, B, and C, as they both use those three values. So having our function in standard form already gives us those three values. So one information is easy to see would actually also be just the values of A, B, and C, which are required for some of the formulas when working with quadratics. Now, for the second option here, we have vertex form, which is our A times x minus h squared plus k. So I hope you know right away what information to see is easy to see here is the vertex, as the name is vertex form. But let's follow through with our fill in the blanks. So same thing here. A tells us the vertical stretch or compression, and it also tells us the direction of opening. And we also know that the vertex is at point HK, which is directly from the equation, and this vertex tells us the maximum or minimum. And how we find that is using A and the vertex itself. So when you know it's your parabola is opening upward or downward, you can determine if your vertex is a maximum or a minimum. And the axis of symmetry we know falls or the vertex falls on the axis of symmetry, so they share the x value. So we have x equals h as the equation for our axis of symmetry. And this is best when we need to find the vertex. It is also really helpful for us when we are graphing because, as you remember, when we began working with vertex form, we started with transformations. So from vertex form, it's really easy to see how many units the parent function of the quadratic moved left or right. From K, we can see how much it moved up or down, and from A, we can see the vertical stretch and compression as well as the reflection in the x-axis. So it tells us pretty much all the transformations, and it makes graphing a little easier for us. Finally, we have our factored form, and what information is easy to see here are the zeros, which occur at points x equals s and x equals r. And if you remember here, we are using that zero identity property, which tells us that if x minus s times x minus r is equal to 0, which is what we are finding when we are looking for the roots or the zeros, then either x minus s has to be equal to 0 or the second bracket x minus r has to be equal to 0. And if you set those as equal to 0 for one solution, you get s, and for the other solution, you get r. And the axis of symmetry can be found from this function by s plus r divided by 2. So considering the roots are at s and r, then we know the axis of symmetry is between the two roots, so it will be between the average of them, so s plus r divided by 2. And this is the best for us when we need to find the roots or the zeros or the x-intercepts. So any of these answers here would have worked. Okay, so that's a little cheat sheet for all the forms of the quadratic formula. So now you know when they're best used for. So this is a great way when you have word problems to know which one should I start, or which one do I have and which one do I need. So now let's look at this example where for now, for this lesson, we're just going to be analyzing those key features that we saw on the first page. And in later lessons, we'll see some of the real world applications. So here, 2x squared minus 8x plus 6. So you're asked to find the direction of opening, the vertex, the y-intercept vertex roots, axis of symmetry, intervals of increasing or decreasing, and you're asked when does the function intersect with line y equals 16. So for the sake of just showing you, I'm going to actually start by changing all of these to, or changing my original function to all of its form. So factored form and vertex form as well. So for factor form, I have a greatest common factor here. So I'm going to start with that. And then here I will test if I have two numbers whose product is A and C, A times C, so 3, and their sum is -4. And these two numbers will be x minus 3 and x minus 1. And you can always do FOIL if you're unsure. So I would get x squared and -3x. Oh, -3x as well as -x, which are going to give me -4x, and the last two terms multiplied will give me +3. And that is my factored form. And now for my vertex form, I have to start with that factoring of the greatest common factor because we want to complete the square. And let me just move this a little over. But we are only completing the square of the quadratic inside the bracket. So here you should see that we need, so if you remember the formula, we divide b by 2. So 4 divided by 2 is 2, and we square that. So in this case, it would be +4. And we also subtract 4 to keep the equality. And we had that +3 there. So now this one, uh, these first three terms are going to be my perfect square. So they need a bracket of their own, so that's why I switched to the square bracket for my first bracket. So here we have x minus 2, because b is actually -4. And this is squared, and we are left with that -4 and +3. And if you just simplify that as well, and this part is like you could have done these two in one step, but I'm just showing you. So here we have x minus 2 squared minus 2. So now let's try to answer all those questions. So the direction of the opening we get is that one we actually just could tell from the standard form. We didn't need to do anything for it. So A is 2, which is greater than 0, therefore upward. You should try like writing your full sentence. The direction of opening is upward, but here I'm just doing a little more faster. And our y-intercept here, this one you can also tell just from the standard form because our y-intercept is when x is 0. So by setting x as 0, the first two terms are just simply 0. So we are left with y equals 6 when x is 0. And yes, you do have to write this part to show me that you understand that the y-intercept is x is equal to 0. Or in other words, you're showing me your work that you chose to set x is 0 to get that y-intercept. Now for vertex, I'm going to switch to the vertex form now. And here I have h is 2 and k is -2. And keep in mind that it's in vertex form, we have x minus h. So h itself is just 2. So our vertex, being hk, is 2, -2. And so we go back for vertex, we have 2, -2 from the vertex form. And I showed my work at the bottom there by showing H and K, so that would be showing your work. The roots we are going to find from the factored form. So here, we are going to set x minus 3 is 0 to get x is 3. And here we are going to set x minus 1 is 0 to get 1. Yeah. And so the roots would be x1 is 3 and x2 is 1. The order doesn't matter. You can write x1 is 3 and x2 is, or x1 is 1 and x2 is 3. Now, our axis of symmetry, so first way, if you recognize it, you know that our vertex falls on the axis of symmetry, so it should be x is 2. You might have also seen it as the axis of symmetry falls between the roots, so 3 and 1, and if we find the average, you will also get 2. Now, interval of increasing or decreasing. So generally with parabolas, we have these two shapes. And I don't really, for intervals of increasing or decreasing, the placement on the Cartesian plane does not really matter in when we're like looking at if we've been translated how many units left and right. So for purposes of analyzing, I can just use these. And you will notice that if I have a vertex here and a vertex here, all these values leading up to the vertex are one of the intervals. Our turning point is always the vertex, and the other side of the parabola is your other interval. So in parabolas facing downwards, we start with a increasing interval, and then at the turning point, so the vertex, we switched. So now we're going downwards, so we are decreasing. And in parabolas that open upward, we start with decreasing, and at the vertex, our turning point, we begin to go upwards, so increasing. So in this parabola where we know that we have a direction of opening up upward, so this is that second example here. And now I know that my vertex is at 2, -2. That means that all values of, so let me just do increasing and decreasing. So if you just label them like this, then you can just write the intervals and I'll understand. So here we'll do, I just need to move this up. So x in the real numbers. So increasing would be all values of x greater than 2. Oh, curly bracket. So here I want you to try to think why 2 specifically. And you should have got that it comes from the vertex, right? So we are looking at the values of x up until the vertex, which are, or after the vertex in this case, because we're looking at the increasing. And all of these are positive, so they're increasing. And however, this way, leading up to x is 2, is our decreasing. Okay, and x is equal to 2 itself is our turning point, so we do not include it. And now our last problem here is when does the function intersect with the line y equals 16? So here we are just setting y to 16, which gives us 2x squared minus 8x plus 6 is equal to 16. And then I'll move this over to get 2x squared minus 8x minus 10 is equal to 0. And now I have a quadratic function that is equal to 0. So this one looks like friendly numbers. I'm going to try to factor it. So start with factoring out that 2. So we get x squared minus 4x minus 5. And then you should see that this itself will be factored to x minus 5 and x minus, or x plus 1. And then we have x is 5 and x is -1. Therefore, the function intersects with y equals 16, or I'm sorry, 16 at points. And so here, because it's points of intersection, we write the point, so 5, 16, and -1, 16. Okay, and you can always double check this with a graphing tool, so make sure you got the same answer. And you have some practice problems for this lesson as well. So just again, focusing on key features of quadratics. And if you want more examples, you can always go back to the examples we have done where we graphed or where we analyze some of the key features like vertex or roots and see if you can make connections between the lesson today and those problems and their solutions. And as always, don't hesitate to reach out if you have any questions, and I'll see you all next class.